Hello everyone, welcome to the new class of solid state physics, and today we are going to discuss a new model that was a correction or a betterment over the last model. So in the last classes we discovered that how Drude's law was very phenomenal. So let us do a little bit of recap of what we studied or what we discussed last class. So what we discussed is um, so recap, what we discussed is Drude's law and how it's um, it unified the language of electricity and heat, but it assumed electrons as classical gas, assumed electrons as classical gas, classical ideal gas, classical ideal gas, not or, but yeah, it's classical and ideal gas. So, what were the successes of Drude's model? So for large scale phenomena, we got success. For example, plasma frequency, um, conductivity, Wiedemann-Franz law. Let us write it in acronym. Wiedemann-Franz law. These were more or less the successes of Drude's law or Drude model. But what were the failures? So the failures were obviously the heat capacity, which was a catastrophic failure. Heat capacity, magnetism would not exist if the classical model is true. Uh, then the velocity of electrons, mean free path, also the temperature dependence of heat capacity, temperature dependence of velocity of electrons, and also the mean free path. These were big failures of the Drude's model. And when the quantum theory, so we have to again look back at the history, because Drude's model came in the 1900s, and now in 1920s, till 1920s, people don't really know that why the heat capacity is broken. People are using the Drude's law to actually do stuff. For example, it gives a very good approximation for the conductivity, it gives a very good approximation for the plasma frequency. So people are doing stuff with that. But in 1920s, what we have is we have a new model called a Sommerfeld model. So 1920s is the era of the development of quantum, of this is called an old quantum theory. Okay, but in 1926 we got the quantum theory. So quantum theory was maturing, it was being more and more matured. Now in 1920, around 1927, Sommerfeld published his work on the Sommerfeld model. It is just like Drude's model. It is again trying to explain what the electrons do in a solid, but it has a different approach. It has like completely different approach, and it gives better results for heat capacity, for velocity, and also for Wiedemann-Franz law. Even like Drude's law was like more or less successful for Wiedemann-Franz law, but for wrong reasons, as we saw in the later last episodes, that there were two opposing errors which were cancelling each other out. But it's not the case in Sommerfeld model. In Sommerfeld model, we will see that the underlying assumptions of the electrons, they're completely different. So today will be a very introductory and short episode about why and how Sommerfeld model is different than Drude's model. So we will do what? So we will actually discuss a Sommerfeld model in a little bit detail. So what Sommerfeld model says is that electrons are not classical particles. Electrons are not classical particles. But what electrons are? They are quantum particles. So they don't follow the rules of classical mechanics, but they follow the rules of quantum mechanics. And what is quantum mechanics say? That there are like lot of electrons. This is the Drude picture. So it's like a gas. Everyone has its own velocities. But the quantum picture is that there are levels, energy levels, and the electrons are filling up on these energy levels. Here, the energy is kind of, like, and there are energy levels here which are not filled. So here the energy levels are continuous. So the probability distribution is like this. Here the probability distribution will be filled, 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 filled. Suddenly it will drop to zero. So wherever it goes from occupied to unoccupied to vacant, so the probability distribution of electrons itself is changing. So here it's Maxwell-Boltzmann distribution. It's called Fermi-Dirac distribution. So Maxwell-Boltzmann, it's called Fermi-Dirac. Okay. So um, now what happens is that Sommerfeld model says that instead of a lot of electrons, so here, okay, so one more thing is uh, to differentiate mathematically how is Maxwell-Boltzmann. So P of E proportional to, so probability of an electron being at energy E is proportional to minus E by kBt. But here P of E is proportional to 1 by e to the power E minus mu by kBt plus 1. So that means that it becomes 0 when E is like greater than mu. If T is very very small, it's like, so T is almost 0, and if it is E is less than mu, then P becomes 1. So it's a step function. So these are the mathematical definitions. So what is Fermi-Dirac basically saying? Fermi-Dirac is saying that, let's say there is a blob of electron. Instead of that, every electron is moving and every electron is conducting heat, electricity, and whatnot. That is not true. That is what is like the all electrons carrying heat and all electrons carrying uh, electricity. That is something being told to us by Drude's model, but Sommerfeld model is saying that most of the electrons are in lower energy level. So let's say this is a circular energy thing and there are levels. So there are electrons here, electrons here, electrons here, electrons here, electrons here. So what they are saying is that there are electrons, but most of these electrons are locked into lower energy states and they can't really do anything. They can't move. They can't absorb heat. They actually cannot they carry electricity also. So what it says is that another simpler look would be, let's say these are the occupied orbitals, these are the valence orbitals. So these are electrons filled. Here what happens is when you give temperature, when you give heat, some of these electrons might jump here, and these electrons are the electrons which will carry electricity and heat. So what will happen is, so instead of all of these electrons, they are dormant. So that is the main difference between Sommerfeld model and Drude's model, and that will actually correct all of the errors that Drude had. So how does it correct the error? So for example, the heat capacity error, right? Drude predicted it's 3 by 2 n kBt per electron, and that was too high. So experimental value was a lot less than 3 by 2 kBt per electron. Oh, and why was it like that? Why did Drude like grossly overestimate the heat capacity due to electrons? It's because he assumed that every electron is participating into heat transfer. So let's say this is a blob of electron which is being approximated as a classical ideal gas, and it's saying that every electron every electron is carrying heat. So and also uh, it's actually not kBt, but it's kb 3 by 2 kb, so that's a mistake, and that is independent of temperature. So there are two problems. One is it's too high. First problem is 3 by 2 k 3 by 2 kb too high, and in low temperature Cv actually depends on T. So what it means is neither it predicts this, neither nor it predicts this. So what happens is like it's completely wrong. And why we saw that, why is Drude getting a very high value? Because he's incorrectly assuming that every electron is carrying heat. But the problem is what now Sommerfeld model is saying, let's say these are the energy levels which are occupied, these are the energy levels which are unoccupied, these are the electrons. So for example, this is the probability distribution. It is 1 1 1, then it suddenly goes to 0. But yeah, sudden, like it's sudden, but there is a slope, small slope. So this region is like half filled or something like that, right? So Sommerfeld says that these electrons are doing nothing, they are dormant. So he calculated the heat capacity, and he got that it's like around experiments. So it's a lot lesser, because most of like 99% of the electrons are not carrying heat, only 1% is. So he got the correct result for heat capacity, and he also showed that if you increase the temperature, what happens is the curve will like look like this, start to look like this. So it will flat out, so it will be, there will be more electrons which will actually go out in the conduction states, and they can carry thermal energy. So he could actually predict that Cv is proportional to T at low temperatures. At low temperatures. So that is something he also could predict. So this is a success of the Sommerfeld's law. And another thing would be the electronic velocities. What Drude predicted is the electronic velocity would be proportional to delta T, which is incorrect. And also the electronic velocity will be around um, like it will be, it is very very low compared to experiments. So and what Sommerfeld says, VE is constant, it's not dependent on temperature, more or less. Why? Because he's saying that the VE will be dependent on the energy of the electrons which are actually carrying stuff. So let's say this is the Fermi-Dirac distribution, and here we have the VE, or the electrons which are actually moving. So this is irrespective of temperature, this is fixed. For example, we have higher temperature, what will happen is the distribution will now look like this, but still most of the electrons will be concentrated here. So to first order, the VE, or the energy which is like directly one to one related with the energy of the Fermi, like the electrons which is at the edge of the conduction, or the like vacant and the filled bands, energy bands, they, it is the same, it's like not varying with temperature. For example, so just to be more clear, what we can have is, let's say this is, let's say T is 1 Kelvin. This will how the curve will look like. This is, let's say T is 5 Kelvin. Let's say this is T is 10 Kelvin, and so on. So no matter what the temperature is, you will get some electrons to jump out, sure, but most of the electrons will still be concentrated here, and there's a very short tail. which is like not very significant. So what we get is that this will be the majority, and that's what the VE will be constant and non-dependent on T, and it will be very high compared to Drude's law. Okay, so what it means is that um, it's two different things. It's correcting actually two different things. So it's not only correcting the high velocity, so it's making the velocity, sorry, it's not only correcting the low velocity, so the Drude predicted low velocity, and it's making the velocity high. Velocity goes high in Sommerfeld. And it says that unlike the Drude's prediction, which predicted the VE or the electronic velocity will be directly proportional to the root of the temperature, Sommerfeld says that there will be no dependence on temperature. Okay, so VE becomes high and the CV becomes low in Sommerfeld's law, because Sommerfeld says that Drude incorrectly assumed that all of the electrons are going to participate in the heat conduction, which is not true. Only the surface level electrons, which are just at the boundary of conduction and valence bands, or filled and empty bands, they will be the one which will be carrying electricity or current, or heat. So what in from Drude to Sommerfeld, VE increased and CV decreased. So when we calculate the Wiedemann-Franz law, then it had, for Drude it was units, and in the same units it would be around 2.44. So it would be around 3 by 2 kb by E square. It would be pi square by 3 kb by E square, and this is far more accurate for most metals, for most metals, or for most materials. So that is a very good improvement on Drude's law. And so what we discussed in today's class was not the mathematical integrities of Sommerfeld model, but what we discussed is what is Sommerfeld model and how it is differing with from Drude's model, and how those fundamental differences in assumptions can actually lead to like pretty interesting and different behavior, and which are consistent with experiments. And so it gives us a better values for everything, and it also does not do like Drude, which had an error in this and this, which cancelled out together to give us the correct Lorentz constant. This is called the Lorentz constant. So that is not something that Sommerfeld is doing. For Sommerfeld, both Lorentz constant and also the electronic velocity and CV, all of them are experimentally nearby values. So next class what we will do is we will discuss more about the mathematics of Sommerfeld model and the mathematical integrities and some derivations, and from that we will gradually move on to crystal systems and how in crystalline systems electrons behave. So see you in the next class. Best of luck, and looking forward to see you all.